Okay, so in this video, we're simply going to focus on restricting the domain and also how it affects the range. So this will be done with respect to linear functions and quadratic functions. So the first illustration I'll give you is a linear function. So if I was to give us something that looks like this, let's say this is a y, or rather f of x is equal to this expression here, then they tell you to say the domain is just greater than or equal to 2, for instance. So you first of all have to plot this, and if we were to plot this, it will be easy to see that the y-intercept and the x-intercept will be gotten when we alternate the zeros. So we put 0 on x and we put 0 on y. If I put a 0, this becomes that. If I put a 0 on y, this is going to be a -4. So you end up having a function that looks like this. You have 0, 12, and you also have a -4, 0, which then gives us a line, a straight line that just looks like this. It passes in these points. Yeah, so I'm just going to start with a dotted one first. So this is the line that you're having passing in these points. Now, the domain was specific. They just want the line for all portions that are greater than or equal to 2. So meaning x is equal to 2 is somewhere there. So if you put 2 in the expression, you notice that you get something like a 6 plus 12. This is just going to give us 18. So this is somewhere there. Let's say 18 is there. So the part that they want is where x is greater than or equal to. So instead of writing, or rather drawing the whole line, we'll just sketch the part which has x, which is from x is equal to 2 positive. They just want this side, right? This is what they want. So this is the only part of the line that we're going to show. So we'll end up removing the other portions that are not needed because they're not part of the domain. So this is going to be your illustration. Let me just write it there. Because it's closed, they said greater than or equal to, so we'll close it, then just go like that. This is the straight line, y is equal to 3x plus 12 for the domain, which is greater than or equal to 2, meaning the range also is going to be greater than or equal to what? 18, because all y values start from 18 going up. So this is basically what you see in terms of them restricting a domain. So the same applies for quadratic functions. Remember we said, or rather we discussed to say, all quadratic functions have a well definite domain. So domain is always going to be all real numbers. That's a general case because these are defined everywhere. No number, no x value can make a quadratic function to be undefined. And the range, we said, depending on the case that you are having. So if a is greater than 0, if the coefficient here is greater than 0, the function will be y is greater than, the range will be, so this is the range, will be 4ac. Y should be greater than or equal to 4ac minus b squared over your 4a. Or you can say if a is less than 0, this will just be your y is less than or equal to your 4ac then minus b squared over your 4a. This is what you can get. Now, how about you look at this illustration that you're seeing here? Look at question number 17 from the term sheet for 1100. So they've given us a quadratic and the domain has been restricted to only be there in between -infinity and what? And 0, and it's open at 0. So we're just saying the domain has been definite. So this is just given like this. This is our domain. Instead of using the whole real line, right? They've just selected a certain portion. So once you restrict a quadratic function, it becomes a one-to-one expression. So initially, these quadratic equations are not one-to-one because for every input you get 2 outcomes. So it's like you saying y is equal to x squared. I'll just give this as an example. If I ask you to say, or rather I'll say f of x is equal to x squared. If I ask you for f of -2, you notice this gives you the same answer as you plugging in f of 2, right? This is just going to be that. You get the same outcome. This is both. This is 4. So meaning this is not a one-to-one, because if it was one-to-one, it would be unique, but this guy is not unique. You put in a number there, whether -2 or you put 2, they are both going to give you the same outcome, which is a 4. So they are both being matched to the same number. So this is not a one-to-one. A one-to-one, the way you can test whether a function is one-to-one is by drawing a horizontal line. A horizontal line should not touch the sketch of the function twice. So if you try a horizontal line, you are seeing we are touching the curve at 2 particular points. So meaning it's not a what? A one-to-one. Yeah, so like this guy here that we're from drawing, this is a one-to-one because any horizontal line you put only touches the line at one particular point. Yeah, so this is what you are having. Yeah, but if you restrict the domain and select only a portion of the curve, so like if I say x is less than 0, meaning I'm ending here, y is equal to x squared, the domain is x is less than 0, meaning from 0 going this side, the other part has been eliminated. So it was supposed to be a whole quadratic, but this portion is not part of the domain, so we ignore it. So we just have this portion this side, and if this is what we are having, we're simply going to be able to even get the inverse. This is what they're asking us in this question. They are saying, find the inverse of this guy, stating clearly it's what? It's domain. So how do we get the inverse of a function? You did this. Inverse of a function, you let a y be equal to the expression. So y is equal to your 2x squared minus 3. Then here you have y, then plus a 3 is equal to, then 2x squared. You can divide by 2, divide this side by 2. So this is simply y plus 3, then over 2 is equal to x squared. Then now you can square root and also square root. Now, because x is supposed to be definite, it's coming from the negative part, so we're just saying this will be this over that, meaning the inverse, f inverse of x is just going to be the square root of x plus 3, then over 2. This is what you get. So you will notice that the values of y in this type of expression is simply going to be, because if you write this is the same as root of x plus 3 and root of 2, so you can have something like that. So meaning the domain of the inverse is what? The domain of the inverse is all real numbers, because any number that you put, we can just say, before we even talk about all real numbers, you focus on the inside part. The denominator is okay because it's always going to be the root of 2. Now the top part is the problem, because x is only seen to be in the top part, because I want us to get the inverse and then state its domain, right? So we solve the inside part. We're just saying, provided x plus 3 is always going to be greater than or equal to 0, then we are okay with it. So x is equal to greater than or equal to -3, because this is okay. It can become a 0, not we're saying greater than or equal to 0, because if this whole thing becomes a 0, 0 divided by root of 2 is just 0, right? So meaning the domain of the inverse is from -3 up to positive infinity. So this is what you'd get as the domain. So it answers the part 2. And like I said, we are only able to get the inverse because the domain was what? The domain was restricted. If it was not restricted, here would have been putting plus or minus 2 when getting the inverse, which is a bit wrong, because we cannot have alternatives to say it can either be plus or minus. Yeah, so we let it just be positive because it was well defined. Yeah, and the reason why we are doing this is because if this guy is well defined, meaning let's say to look like it touches -3, it's supposed to look like this somehow. So all the values of what? All the values of, this is -3. The range of this function was supposed to be from -3 going up. So if you pay particular attention, you'll notice that the domain of the inverse is equal to the range of the original function. Remember, we said this when we were doing the topic, to say sometimes how you get the range of a function you have to get its inverse first. Then the domain of the inverse is going to be the range of the original function. And you're seeing that this is matching up with that theory that we learned. Okay, so this being said, we can now look at the last question here, which just requires us to get the values of a. So they are saying the values of a for which the original function at a, so we put a in this. What is f of a? Meaning we put a, so this is just going to be a squared, then minus 3. Then f inverse at a is simply going to be, we put a there, so this is going to be the root of a, then plus 3, then over the root of 2. So here they want us to get the values of a for which the original function at a is equal to f inverse at a. So we'll simply solve them like this by equating them. So we'll put 2x squared minus 3. This is 2a here. This is an a. We're just getting this expression and putting it there. Then equate it to the root of a plus 3. Then over the root of 2. So this guy here is simply going to be, so what would have done here is by squaring both sides if you wish. So we can just square both sides so that we turn this into a polynomial. That's going to be 4a squared minus, that's going to be a 12a squared, that's going to be a 9, is equal to, this will just be a plus 3, then down you just have a 2. So I just multiplied this by itself. So this is going to give us that, and that will give us that. Then this will give us a positive 9. Then from here, we can now cross multiply. So if we cross multiply, you simply get 8a squared minus, oh, this is 4 here. This has to be a 4 here. Yeah, so pardon me, this has to be a 4. Yeah. So this is a 4. This will be 24, because we're multiplying with this 2. So this will be 24a squared and plus 18 is equal to a plus 3. Then this now becomes 8a4 minus 24a squared, then minus a plus 18 minus 3 is equal to 0. This is 8,4 minus 24a squared minus a, then this is plus a 15 is equal to 0. Yeah, so now at this particular point, the expression has a power of 4, meaning this is a polynomial, and the best way that you can solve a polynomial is using a trial and error method so that we get its roots or its solutions. Yeah, so this is simply going to be, we look for a number that we can put in the whole expression to give us, to simply give us a 0. So we can start with a being equal to -1. So if you put, the only way you can know the numbers to use is to focus on the constant. So you focus on the factors of 15. So what numbers can go in 15 without leaving a remainder? So there's 1, 3, then there's 5, then there's 15 itself. Now you'll be trying both the positive one and the negative one. So in all the cases. So if you try -1, this is going to be that's going to be +1. This is going to be 15. If you check this, so if you check this, it simply becomes a what? It gives us a 0. So this is a factor. So a is equal to -1, or rather put, we can say a plus 1 is a what? Is a factor. So this is the first factor that you've gotten. Now you're going to use synthetic division. Put this -1 somewhere here and get all the coefficients of the expression that you had. So this was 8. The next one, there was supposed to be an a to the power 3. We need to put it in a way that will match the descending order of the variable a. So the coefficient of a to the power 4 is 8. The coefficient of a to the power 3, there was nothing there, so we put a 0. The coefficient of a to the power 2 is -24. The coefficient of a is just going to be -1. Then the constant is what? Is a 15. Then this will simply bring down the 8 here. Then this times -1 times 8 is simply -8. You add this. Then this times 8 is going to be that. This is going to be -16. That's a 16. That's going to be a 15, -15. This gives you a 0. So this leaves us with 8. So the 8 that we are having here will be raised to the power 3 now, then minus 8 to the power 2, minus 16a, then now plus a what? Plus a 15 again. So now we have this guy here. Again, we break it down. We're going to look for numbers such that this whole thing here becomes a 0 again. So this is a plus 15. Okay, so we are having the quotient that we're getting is this quotient when we divide the a plus 1 into the actual polynomial. So we're getting this is equal to 0. We have to break this quotient again the same way that we did. Now we're looking for the possible factors of 15 are simply plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So if you get to attempt all these guys in the expression, I'm getting that none of them is giving me a 0, so implying that the only solution, so the only root of f of a is equal to f inverse of a is just that a is equal to a negative 1. So this is the only value that I'm getting. The other part is going to give us what we call miscellaneous equations, those solutions, those solutions that are not actually part of the expression. So you can confirm, or we can always try to check if our answer is close to the truth in terms of the relation between f of a and f inverse of a. So f of a was 2a minus 3. This is equal to root of we're having root of a, then plus a 3, then over root of 2. So this side, the left hand side, we can try to replace. If we put negative 1 squared minus 3, this should be, will end up being that. Then the right hand side, if we were to check this, this is equal to this side, we're going to get what? This is the root of negative 1 plus 3 over root of 2. So this is going to be equal to root of 2, then root of 2 down. Now, because we can either accommodate a positive or a negative outcome, and we are looking for something that will suit up this, so this will still give us what? A negative 1, because anything from the square root can either come out to be positive or negative. Now we're interested on the negative part, because this aligns with the domain that we initially put, because all x values must be less than what is 0. So that's the reason why we're saying we're picking this to be a true value of a for the relation between f of a and f negative. Okay, so I just wanted to stress the whole importance of restricting the domain. That being said, I will see you in the next video where we look at all the questions from the 1100 tutorial sheet. So thank you so much for watching.